Hi everyone, we're Team 18 and we worked on a project for a Morse code interface, and we're going to talk about how our project went and the code that was involved in it.
So this project constitutes a Morse code interfacing functionality for the Nexus A7 FPGA board. It encompasses the use of a VGA, an external keyboard, and the board's 7-segment display. With the help of the VGA, shapes corresponding to the dot and dashes of a Morse code are visible to the user. The keyboard is used for the user input as a guess for the corresponding Morse code on the screen. And finally, a 7-segment display is used as a visual aid for the user to see the word shown in Morse in the screen.
Yeah, so we worked on this project for some time, and although we weren't able to accomplish what we were hoping to have by the end of the deadline, we're going to basically cover our successes and failures, what functioned, and what we could work on if we were to make the project better in the future.
All right, to start off, we will be commenting on the Vga Top Module that includes the VGA clock divider, VGA controller, and the keyboard input that Amy will be talking about. To start off here, we have all these inputs. We have the clock, we have the keyboard, clock as an input. We have switches to basically control the Morse code. And we have the keyboard inputs, and we have the signals that are outputted by the VGA controller. So first we start by creating a 25 megahertz clock for the VGA signal to work. This is, here is our module. It's basically we get a 100 megahertz code as input. So we divide it into 4 and we create a 25 megahertz clock outputted as such. So then we have the signals for the VGA controller, the horizontal and vertical signals. Here's a short snippet of this code. And after this one, we assign the values corresponding for the screen to turn on. So as a, I guess as a failure of our code, we were trying to get this automated, but instead we had to end up using switches to basically drive the input of the Morse. So we use a switch for a rectangle as a dash and a switch as a square for a dot. And so here on this case statement, we basically have 7 bits and we're comparing all these switches. We have a switch for a rectangle, a switch for a square, a switch for a green screen, one for a red screen, one for a yellow screen, and a space, and once we're done inputting a word. And this case statements basically just assign the signals for the colors of the VGA screen. And so our basic functionality that we wanted to achieve is to input a Morse code using these switches, and this code would be saved in a register value, which would be this input Morse register that we have initialized here. So every time we input a rectangle, which was a dash, it would add a 0, 1. And if it was a dot, it would add a 0, 0. This is the encoding that we used for the dash and dots for the Morse code. And therefore, every time we click the switch, it would just concatenate it to whatever we had before in that register value, and it will get saved for later use in the keyboard input. Same thing for the spaces and once we're done. So we wanted a space in between each letter, so we have a switch for that and a switch from when we're done inputting the word, and then we want to continue on to comparing that input with the user's guess in the keyboard input. And that's going to be part of the keyboard module that we're going to see next. As part of kind of other failures on this module, we couldn't really get these keyboard input module to run at the time that we needed. It wasn't working with the VGA controller. We tried it with an LED, trying to see if the guess was correct or if it was not correct. We wanted to turn on an LED or turn on a different LED for an incorrect one. This didn't work. We had some trouble with the overall syntax of Verilog, and we tried a few different things, and none of it really worked, even though our logic kind of seemed correct in the sense that we wanted this to happen under only the condition that we were done inputting the Morse code. And now we'll have Amy talk a little bit more about how we did the decoder for the Morse code.
All right, so now we're going to talk about some of the failures of this module. This was supposed to be the keyboard input module. As you can see, we labeled all of the keys and their respective hex code values. Our encoding was supposed to be minimal bit width encoding, meaning that the dot would be a 2-bit 00, a dash would be a 01, a space would be a 10, and then signaling that the word is done would be a 11. Basically, this always block concatenates the new input keys to this complete word variable and adds onto it. And the main issue we had with this was basically comparing the input value with the Morse code value and displaying whether that value is correct or not.
Okay, so this is the Verilog code for the 7-segment display of the FPGA. We have our top module for that. It's called text test. And as you can see, we have the inputs as switches, our output as the 7-segment, and various registers included in that. So if you go down here, you can see we instantiated the counter called text logic. And what that module does is to put together our letters to create the words that are displayed on the FPGA. So as you can see with our 3 switches here, we have a case, which using the 1-hot encoding puts the 18-bit numbers here to create preset letters that are for the Morse game. And additionally, in the text test module, we also have the 7-segment, which is what I used to create the letters. We created letters such as A, B, C, and so on. And you can see how we use the same concepts. Using a hex in a case, we created different combinations of the 0s and 1s to create the different letters, as well as numbers and a blank space.
Go.
So one thing we weren't able to do for the 7-segment display was to have it linked to the VGA, because that was the main goal of our game. So we couldn't have it dynamically linked, and we had to forfeit that, but yeah. Okay, so this is the outcome of the 7-segment display code. As you can see, we have our 7-segment display showing EC311, my favorite course at the moment. As you can see, it's pretty good. We have the last 3 digits. I made sure to have them blank, not necessarily show the 0s at the end, which is really important in having the word show perfectly and without confusion. So as you can see, as I play it, it's going to then, with the push of each switch, it's going to switch the words. So our first word, let's see what it has. We have FPGA, of course, the very device that I'm touching at the moment. So yeah, we tried our best to have each letter show as well as possible. Some letters are hard to display. So for example, G may look like a 6, but we tried our best to have it the best way we could. So as you can see, EC311 is the default mode when it switches off. And if you go back a little bit, it says burger. You know, everybody loves burgers, so that's good. And last but not least, Verilog. So yeah, that's basically how we're able to involve the FPGA text display in our project.
As a quick visual aid demonstration, we were really not able to show exactly what we wanted to show, the automated Morse and the green screen, red screen, depending on the correct guess. We tried many things, and it could only work separately on its own. So I want to show what we had before it kind of broke down after we tried to put it all together. And here is just a video of how me with touching the switches, we can see a rectangle for a dash, a square for a dot, and either a green screen or a red screen. This is just basically the VGA controller. And we can see green, green, rectangle, dot. And this is basically how the Morse code would go. And in the end, we just see a green screen for correct, red screen for wrong. And this was mostly all I could accomplish with the VGA. I hadn't worked on this before. I wanted to show the text on the VGA, and I tried many different things to do this with memory and the ROM files. I tried with sprites, so really difficult topics that I give it my best to understand and try to work out. But after several tests with this, it didn't come out as expected. So here's just a little video of what we could accomplish for this class.